Hi there, welcome back to this channel. In this video, we are going to be seeing the magnetic effect of electricity. So far, we have you've been introduced to the concept of magnetism. So now, and you see that it is under the series of our electricity videos that we have been introduced to magnetism. So now today we are going to be looking at the relationship between magnetism and electricity. Now, it happened that it was in 1820 that the link between magnetism and electricity was established. And it was first done by a particular scientist known as Hans Christian Ørsted. Hans Christian Ørsted. He was the first person to prove that magnetism and electricity are related. And how did he do this? Now, what he did was that he saw that a current carrying conductor, that is a wire in which current is running or through which current is running, had magnetic field around it. How did he do it? Some sources have it that he stretched a compass needle. The compass needle contains a magnet, right? That needle that turns in a compass contains a magnet, yeah? So he turned a compass needle towards the direction of a wire that current was running through. And he saw that compass needle deflected. Then he decided to change the direction of the current that was running in that wire. Then he stretched it towards it, and he saw again that it deflected. Now, some sources say that that was not the experiment he was performing that day, but he claimed that was the experiment. It was somewhere between 1819 or 1820. Is that okay? All right. So the idea is that he was the first person to find out that to observe that a current carrying conductor had a magnetic field around it. Is that okay? So this was the idea that if I have my cell here, my battery, is that okay? Now, and I have this loop of wire. This is just a conductor. Where will the direction of current be? In this place. Up here. This positive end now. This negative end. So current is going to flow in this direction, right? Down here, in this direction here, and up here, right? Good. So current was running like this in that is experiment, and then he stretched a compass needle towards it, and the needle deflected in a particular direction. So now, the direction in which the needle deflected can be gotten, the direction of the magnetic field around it now, is that okay? Can be gotten using what we call the hand rules. The hand rules. So the hand rules, we have about 3 to 4 right hand rules, 3 to 4 hand rules that I'm going to teach you. Is that okay? For different things. So for this case, the most basic hand rule that we're going to be using is the one that we use to check the direction of deflection of that compass. Is that okay? So once I stretch the compass towards it, it's going to deflect in a particular direction and deflect in a particular direction. Is that okay? So what we noticed was that the compass, the magnetic field was actually around it. So with that, we have the first right hand rule. So the first right hand rule goes like this. If my current carrying conductor was like this is my current carrying conductor. If I wrap my hand around it, my thumb on it will represent the direction, my thumb on it will represent the direction of the magnetic field. Is that okay? My thumb on it rather will represent the direction of the current. Do you understand now? My thumb on it will represent the direction of the current. Direction of current. How do you draw this? Sorry. Is your hand as fat as this? Or something like this, right? Okay. So roughly like your hand, right? So if the current, this is for when the current is flowing up through the wire, flowing in upward direction. That when it's called the clenched fist the clenched fist rule. Is that okay? So this rule says that when you wrap your hand around the wire with your thumb facing the direction of the current, the direction in which current is flowing, the magnetic field is going to be the direction of your hand that is wrapped around the wire. So it means that in this case, if current is going up, where is magnetic field going? In this, on this side, this place is not show, this place is not show. So on this side, where will current go? Into the board, right? At the back, in this direction, right? On this side, outside the board, on this side, towards me like this, isn't it? So that's the way it is. So it means that magnetic field, if you check it from the top, will be what? Anti-clockwise. Does that make sense? So what that is saying is this. Now we're going to be using the arrow system of viewing vectors. You know, vectors we represented by arrows, eh? All right, so we're going to be using the vector a lot to view things now. So if I draw a circle like this and I put a dot in it, it means it is coming out of the board. It means you are looking at the top of the vector arrow. Does that make sense now? If you see a circle like this that shows this, it means that what? It is going into the board because this is the back of the arrow. You know, the arrow is like this, somewhat like this. Only you can do, undo, redo, do. All right, so you see this, yeah? So it's going to be like a star when you look at it from at the back. Is that okay? So this one is going into the board, this is coming out of the board. So now follow. So I said that, so when you stretch that compass needle towards this guy, towards that wire, in this case, where is current going to? Current is going down, right? Does this make sense? So if I wanted to chart the path of the magnetic field around this guy, now I'm going to draw, let me draw a paper, a cardboard, is that okay, around this guy. So this is like on this part of this board, how is the magnetic field like? So how do you do it? You hold the wire with your hand going, with your thumb going in the direction of current, right? So your thumb will go in direction of current. You hold the wire like this. Current is going down, so your thumb will go down. So it means that on this side, this guy is going like this. Does that make sense? At the back is going like this. This side is going like this. At the front is going like this. So it means the direction of magnetic field from the top. If you check from the top, that will be what? Clockwise. Is that okay? If you check from under, that will be what? Anti-clockwise. Does that make sense to you? All right. So what that means is that if I have a current running into, where is this? Is this coming out of the board or into the board? Out of the board, good. So if current is coming towards me, so I have a wire that is stretched in this direction that's coming out of the board towards me. So the magnetic field around it, and current is flowing in this direction. It means the magnetic field around it, if I were to hold, so let's say this was the wire now. So if I were to hold this wire, in this case, it means that my magnetic field will be flowing like this. Does that make sense? All right, so my magnetic field will be, in what direction is this? Anti-clockwise. Does that make sense? And if I have a current that is flowing out of the board, that is flowing rather into the board, the direction of magnetic field will be such that, since it's flowing into the board, I will hold it such that your thumb is the major thing here. Is that okay? So your thumb is going to tell you direction of, you already know the direction of current is flowing into the board. So the direction of current, you point your thumb towards it and you clench your fist around the wire, and then you're going to see what looks like this in a clockwise direction. Does that make sense now? All right, so that is basically what we have about the first right hand rule. However, another scientist, gave another idea of these hand rules. Is that okay? Give me, if you can see okay, now look at this. You're going to see this. Now we call it the Maxwell Corkscrew cork. This is cover, right? Corkscrew rule. Is that okay? I think it's corkscrew. Maxwell Corkscrew rule. Now his rule is saying that, now this is a cork. This is a cork. Cover. Is that okay? Now, if I put this in here, if I turn it in this direction like this, rightward direction, where would this cover be moving? Bring that bottle, please. Only you can do, undo, redo, do. All right, now look at this. Now, look at this now. This is my cork, but the cover, right? By the time I turn it in, what direction is this? Clockwise, right? Now, my hand is going clockwise, but where is the cover going? The body of the cover? Down, right? The cover is going down. So it means that if the current is going, so that will be the direction of current. If the current is going downwards, it means magnetic field around it will be what? Clockwise. Does that make sense? Then if I'm losing it, that's for a right hand cork. Is that okay? If I'm losing it, where will this cork be going? It will be going up, right? But where is the direction of magnetic field around it? Anti-clockwise. Does that make sense? So that's the Maxwell's Corkscrew Rule. Is it clear? All right. So now, so we know the right hand rules now, right? The first right hand rule. This is called the first right hand rule. So if I were to draw a system like this and I said, come and arrange for me the directions of this guy, of these compasses. If I told you current was going up in this wire, I now show you compasses. Let me say, I don't want to draw the current on it. Let's say current was going up. Is that okay? Let's just say this wire, current is going up. I now show you if the first compass, compass A like this. This compass A, let everything face up. Let everything face up. Compass A, compass B, compass C, compass C, compass D. Now, and I said this compass A, think of it as being on top. Compass C at the back of the wire. This one, compass A, at the front of the wire. While compass D and compass B are on this side. Compass B is on this side, compass D is on this side. But this one, they are at the back and at the front here. So while D is here, B is here. If current is going up, where will be the directions of these compasses? Compass A is at the back, is at the front, compass C at the back, compass B at this side, compass D at this side, around the wire. Anti-clockwise, right? So where will compass A turn? Compass A is at the top here, at the top of the wire. So where will it turn? Will it turn this direction, this direction, this remain this direction? Which direction will it turn? The compass A. Now look at it. Compass A is in front here, right? So first check the direction of the magnetic field. So magnetic field is going to be around like this. So by the time you get to the top here, this compass will have turned in this direction. So by the time this current begins to run here, compass A will turn in this direction because it's in front of the wire. Is that okay? Compass C that is at the back of the wire, where will it turn? Yeah, it's at the back of the wire. Where will it turn? This direction? No. It's going to turn this direction because magnetic field is going like this. Do you understand now? Does that make sense to you? It's going to turn in the direction of the magnetic field. That's the point. So magnetic field is going right around. As you turn around like this, right? This hand is going like this, right? So it's because this guy is at the back, it's going to turn in that direction. Does that make sense now? This one is on this side. Where will it turn? How will it face? This compass is on this side of the magnet, of the wire. So where will it turn? Okay, let's do it. So this guy is turning like this. This guy is going like this. So on this side, what is happening? It is entering the board. Does that make sense to you? Are you sure? Does it make sense to you? Compass B is on this side, on the right side. So on the right side, where is magnetic field going? Magnetic field is going into the board. If you look at this is our wire. Magnetic field is going into the board. Does that make sense? So this one is this side here. A, you see? B, into the board, C in this direction towards me, D will come out. God bless you. Do you now understand now? All right. So this is arrangement of magnetic field around the that guy. All right. Now, so it was also found out that the strength of the magnetic field, we call it magnetic field strength. The magnetic field strength, I probably gave this formula in my first video of magnetism. The strength of magnetic field strength, or magnetic field intensity. Another word is what? Magnetic field intensity. It's given by the vector B. Is that okay? It's a vector quantity. It's also called magnetic flux density. Is that okay? Magnetic flux density. And this one is what? Magnetic field intensity. It's given by the formula mu naught I over 2 pi. Does that make sense now? Mu naught is given by, mu naught refers to permeability of free space. That's the value of about 4 point something times 10 raised to the power. I really can't remember, but in your calculations, if you need to solve this, you'll be given the value of mu naught. Is that okay? So it was found out that this strength of this magnetic field is dependent on what? What do you see here? Current. Is that okay? So the magnitude of the strength, of the current. So the rate at which charges are flowing on the wire, or the higher the current in the wire, the higher the magnetic field surrounding the wire. Is that okay? And the closer to the wire you are, the higher the force, the magnetic field, the higher the strength of the magnetic field too that you feel. Is that okay? And the farther away from the magnet, from the wire you are, because the closer to the magnets you are, the higher the density of the magnetic flux. The magnetic flux is just the lines, the field lines. Is that okay? Together, plenty together. So the field lines are closer as you close to the wire. They are closer. So and the closer together they are, the more they are. Does that make sense? And then the more they are, the higher the strength, isn't it? Or the higher the density. Is that okay? So the higher the closer you are to this thing, the higher the magnetic field felt, or magnetic force felt due to the field. Then the farther away from the wire you are, the lower the force felt. Now another thing you should now know is so we know the hand rule now. Another thing you should now know is what was also found out later about the fact that two wires that are carrying that have common current, and if they are brought close together, they can attract each other. Yes, they will attract each other. While wires that have different currents, they will repel each other. So let me show you how it was done. So if a wire now is coming out of the board here, another wire, so there are two wires, one wire is coming out of the board, the other wire is coming out of the board here. If current is coming out of the board now, let's say current was coming out of the board, so you are going to put your hand like this, right? So you wrap it around this. So where is the direction of magnetic field? Anti-clockwise, okay? So we're going to have something that looks like this. Anti-clockwise. All right, this is the direction of magnetic field. Is this clear? Anti-clockwise. So for this same guy, current is also coming out, right? Current is also coming out. So we're going to have something like this, like this, like this, like this. The magnetic field around is what? Anti-clockwise. So you see that if this field keeps expanding, what will happen? What will happen? This guy, they will now coincide, right? So because they are flowing in the same direction, so this is what will now happen. Because they are flowing in the same direction, you now have something like this. So because of that, they will be what? Attracted to each other. Is that clear? So they have similar currents, so similar or like current. Attractive. Is that okay? The force between them will be what? Attractive. But what if they have dissimilar currents? That is currents in different directions. What do you think will happen? They are going to do what? Repel one another, right? So you're going to have something like this. One is coming like this. Let's just say current is flowing out of the board. And this other guy Current is flowing into the board. So magnetic field around this one, just like we had there, will still be like this, anti-clockwise, right? Well, in this case, let's bring it close, away from here. Clockwise, right? Why is it clockwise? It's going into the board, right? So it's going like this. So that will be like this, clockwise, all right? If that's the case, what will happen? This one is coming like this, this one is coming like this. What will happen? The magnetic field will want to touch each other and cancel out, right? And magnetic field lines don't touch, right? So if they don't touch, what will happen is that they will create a neutral point here. You create what? And for a neutral point to exist, then there will be what? Repulsion. The what? Repulsion between the magnets, between the wires. All right, so that is it for the first right-hand rule. Now, quickly, I'll just take you through the other, in the next video, I'm going to take you through all the right-hand rules that you need to know, and do what to subscribe to the channel and see that video. I'm going to link it in the description below. God bless you as you subscribe and share the video with your friends. Now that we know about the magnetic effect of electricity, and that is the fact that the wire carrying current has a magnetic field around it. Now let's make some changes to the system. What if we curled our wire into a loop? We made a loop out of our wire. So if this was my wire, then I decide to turn my wire like this. So it's still connected to a battery source. Is that okay? A voltage source, so that current is still moving in this direction. So this same guy is connected to voltage to a battery, so that current is also moving in this direction. That is, I choose the clockwise direction. Now, for a wire that is made into a loop like this, basically a loop like this, how is the magnetic field around it going to be? So using the same first right-hand rule, if we hold it here, it's going to be into the board on this side, out of the board on this side, into the board on this side, out of the board. So everywhere inside the loop, magnetic field will be into the board, out of the board, everywhere outside the loop, into the board, out of the board. By the time we hold it like this, into the board, out of the board. All right, and that is going to be throughout the entire loop. Okay, so what that means is that magnetic field is going to be in this direction. If we look from underneath this wire, magnetic field is going to be clockwise. If you look from this side, on this side of the wire, magnetic field is going to be somewhat like this, something like this. Do you get that? That's the magnetic field is going to be. So clockwise. Now, what if we increased the number of our loop? Now, so let's say we now made many loops like this. Now, why do we do this? Why do we increase the number of loops? The first reason is this: the higher the number of loops, the higher the magnetic field that will be generated. And I'm going to show you. Now, what do we call a loop of wire? Many coils of wire like this. We call it a solenoid. Now, provided that the same current runs through them. Is that okay? So, we are going to produce what is called a solenoid. Basically, a coil of wire. I'm going to draw the actual representation, but I wanted to show you something with this. So, a coil of wire around something is going to be a solenoid. Basically, if I were to use my charger, a solenoid, this guy here is going to be a solenoid. This guy here is going to be called a solenoid. Basically, I'm wrapping the wire around this guy, and it's going to be uniform. Is that okay? I don't want to destroy the cord. That's why I'm doing that way. Now, you see, so we make a solenoid. Now, what a solenoid does is this: it concentrates the magnetic field and makes it higher, or it tends to increase the magnetic field, because the loop of wires will be very, very close together. So their magnetic field will also be very close together. Do you understand? So what that means is this. If we examine only this part, only this stop, for example, you know that we said that the magnetic field, so let's say this wire now, this wire that was like this, this wire that is like this, now we turn it like this. So imagine we are turning it like this now. We are turning this wire like this. It means magnetic field is going to be where? Clockwise, right? It's going to be clockwise, yeah? Magnetic field is going to be clockwise. If we turn the plenty coils of wire that we have made, if we turned it from being like this, we turned it like this. Magnetic field is going to be like this, right? Now, what you will notice is that this magnetic field is going to have expanded over the entire diameter of this wire, because there are many wires here. Do you understand? So the magnetic field of the first one, that started like this, will add up to the magnetic field of the second one, add up to the magnetic field of the third one, and then more and more like that, and then it's going to create a strong magnetic field that will run in the clockwise direction. So that is how a coil of wire becomes a magnet. I'm going to show you the actual representation. So I have my voltage source here, and then I bring my conductor and make it into a coil of wire like this. So I've made this guy into a coil of wire. So what will happen here is this. Let me first use the crude technique to show you the direction of the current. And we said that this guy, if you remember our video on magnetism, we said that this guy will practically become what? A magnet, yeah? A temporary magnet. And by the way, we use the two words, we use permanent and temporary magnets to mean that this guy, once we switch off the system, if we switch off the system, so this is off now, the key is open, so if you switch it off like this, this guy is no longer a magnet. So electromagnets are temporary magnets. Then permanent magnets are lodestone, magnetite. Is that okay? Alright, so this guy now is a temporary magnet. Once I switch this on, I connect this guy, what will happen? Current will begin to flow in this direction here, in the upward direction here, in this direction here, downward here, upward here. Are you following me? Just follow me, you're going to get it. Upward here, downward here, upward here, rightward here, downward here, upward, rightward, downward, upward, rightward, downward, upward, rightward, downward, upward, rightward, downward, downward here, and back to the negative terminal. Is this clear? It's going to flow in this direction. So just follow the arrows. Now look at what I'm going to do for you. I'm going to show you how to know, because this is going to become a magnet. So I'm going to be showing you how to know the north, differentiate the north from the south. There are two techniques I'm going to be showing you. The first technique is crude, but it will make you to better understand the concept of right hand rule that we use. Then the second technique is going to be a very easy one. Now watch this. Now using the crude technique, if I hold my wire here, where is the magnetic field going to be? Into the board here, outside of the board here. So by checking from under, it's going to be what? Clockwise. Does that make sense? If I hold my coil of wire here, at this point here, if I hold it here, using the first right hand rule still, I hold it here, then my magnetic field is going to be into the board and out of the board, right? So if I have these all segments together, what that means is that magnetic field is going to run like this. Does that make sense? Magnetic field is going to run like this on this first wire, on this part of the wire, the same way, on this part of the wire, the same way, on this part. So what will happen is that there's going to be a loop that is going like this that will be created. Does that make sense? So that loop will now overlap and expand throughout this place, and then you're going to have something that is going like this, coming out like this, entering like this, coming out like this. Now remember, in a magnet, magnetic field goes from north to south only outside the magnet. But inside the magnet, magnetic field goes from south to north, south to north, south to north. Don't forget it. Outside, so if I say magnetic field run from where to here, You will ask me where. Is it inside the magnet or outside the magnet? Remember we said that B fields are continuous. They are continuous. And the reason why they are continuous is because inside the magnet, it runs from south to north. Outside the magnet, it runs from north to south. So it creates a continuous loop. Is that okay? The same way we have here, from north to south. But inside the magnet, south back to north. So inside our magnet now, magnetic field is running from where? South to north. So that outside the magnet, it's what? North to south. All right. I hope you got that. I'm going to explain again, but let me quickly show you the simpler approach. Now, here is the simpler approach. So I still have my system. So here is my solenoid. So I switch it on. The system is switched on. Current will run like this. Is that okay? And the same way, current is going here, down, up, here, down, up, here, down, right, up, down, right, up. I hope this is not confusing. Just follow the coil as I made it. So as it's coming here, it's going to be coming down, up, side, down, up, side, down, up, side, down, up, side, down. Does that make sense now? So this is the path that the current will take. Now listen carefully. The second approach is very simple. Now if I took this my coil of wire and I brought it like this, now the direction, so okay, no, look at it this way. If I stay in this direction and look at the direction of current, how is current flowing here? If I look from here, how is current going to flow? I hope that this is capturing. If I stay here on this side of my magnet, how is current flowing? Current is going to flow. If I stay here and look at the direction of flow, because that current is going like that, current is going to flow in this direction, in the clockwise direction. Current is going to flow what? In the clockwise direction. If I look from here, because current is coming like this. No. If I look from here, current is coming. If I look from here, current is coming like this. And like this, and like this. Okay, this is clockwise. Sorry, this is clockwise. Then if I look from here, current is going, because this loop is going to appear like this. Let me make it for you so that you understand. So here's my coil of wire. So here's my coil now. Here's my coil. So current is going in this direction like this. So here's my coil. Current is going in this direction, right? In this direction, coming here, direction, coming here, and up, then down at the end of the day, if this were a long wire. Is that okay? So if this is the case, the side current is going like this, like this. If I look from this side, where is current going? Anti-clockwise, I'm sorry. It's not clockwise. Current is going anti-clockwise if you look from this direction. And if you look from this direction, current is coming like this, so which is what? Clockwise. Is that obvious? So if you look at this thing now, if you look from this direction, this is my coil of wire, right? This is my coil of wire. If I look from this direction, like this, current will be going anti-clockwise. You know my coil of wire, current is passing from here, down to the back, out, down to the back, out, down to the back, then down like this. Isn't it? That's the direction of current. If I turned my loop like this, current will be going how? If current was going from here, it means it will be going anti-clockwise. If you look at it, it's going to be going anti-clockwise here. So where the current is going anti-clockwise, you call it the north. Now where, if you look from here, since current is coming like that, it's coming like that, then it's going to be going what? Clockwise. So where the current is coming in the clockwise direction is going to be our south. Does that make sense to you now? So this is going to be our north, and this is going to be our south. You see, we are correct. Does that make sense? Now, if you usually forget it, Just draw. How do you draw your S? Your S is drawn like this, as if you are going to draw. It's going to go like this. Okay, more like draw an arrow like this clockwise. Is that okay? Then merge it. That is what? That is the clockwise direction, which will be the south. Is that okay? So this is the south of the magnet. Now, what can you do to improve? Now, the thing is that with this magnet is not so strong because just is not very strong. The magnetic field is not so strong in it, but it's stronger than a wire. But if you wanted to increase the magnetic field here, now there are some things you can do. Number one is that you can increase the amount of current. Because remember that we said this formula, B field is equal to mu I, mu naught I over 2 pi. So if you remember this formula, we said that B vector is directly proportional to I. So since it's directly proportional to I, it means that if you increase the current I flowing in the coil solenoid, they are going to increase the magnetic field. Another way to increase the magnetic field is to increase the number of turns. Increase number of turns. Number of turns in the wire. Once you increase the number of turns in the wire, we are going to increase the magnetic field, because the higher the closer and more the field is, the stronger the magnetic the wires are, the stronger the magnetic field being generated. So basically, these are the two things that you can use and that you can do to improve the magnetic field that is here. Those are the two things. You increase the current and increase the number of turns. So this will be it for this video. In the next video, we are going to be talking about motor effect of electricity. Do well to motor effect of electricity. Yes, do well to watch that video. See, just follow all of this my series. I'm going to try to compile it into one playlist. Do well to follow all the series on electricity, because it's fully packed with all the lessons that you need to ace your JAMB. God bless you as you subscribe to the channel and share the content with your friends.